Hi, today I would like to present SAMZA. SAMZA stands for Stateful Scalable Stream Processing at LinkedIn. It's a top tier work. Firstly, I'll introduce what is the stream processing. Stream processing means that the stream means that data in motion. Data is generated in one device and it is transported to the other device. If we take an example of a request response application, for example, you are accessing HTTP, you are like sending a request, and then you are in microsecond, you are just getting the response from the website. So it's very fast. And then if you take example of Hadoop, so it takes longer time to get the data from there. But in the middle, uh, we need to have some processing technique that when the data is generated and we don't have all the data available in batches, but still the data is incoming and we concurrently processing that incoming data and then it is outgoing. And why it is important? It is very important because when, for example, you log into your LinkedIn pages, you are receiving some feeds, some relevant feeds which are interactive. And also, if there is some fraud detected in bank security or anywhere, in real time, that anomaly is detected and it is dealt with. So this kind of stream processing is in terms of second, not in terms of millisecond, not as fast as request and response, and not as slow as like streaming the data for in the batches form, but it is in seconds or at most in minutes. And also the internet of things data, so we have multiple internet of things devices in our smart houses, and they are collecting massive amount of data, and they also need to be processed in real time, almost so in seconds delay. And then, for example, some ads are coming automatically when you are playing some video or gaming, and also some trading applications. All these things are streaming application examples. How the data is processed at LinkedIn, because this paper is related to LinkedIn, so they have only considered the LinkedIn examples. So if you see, there are three layers: the service layer, the ingestion layer, and the processing layers. The service layers, uh, it composed of the websites and the mobile application, where the client interact generates two main types of data that need to be processed. First, more than trillion of events are generated per day. For example, view ads or shared article, etc. And second, an often overlooked source of data are updated to the database. So the ingestion layers, this one layer, it updates the stream of events and ingests them into fault-tolerant and replayable messaging system. The use of large-scale publish-subscribe system called Apache Kafka, which is this one, and the data bus is a database for the messaging system for events and updates. And finally, we have the processing layer. In the processing layer, multiple streams of events and updates are fed to one or many SAMZA jobs. And SAMZA acts as a core processor framework where the processing, which process input and generate the output in real time. So what is the scale of processing at LinkedIn? Since LinkedIn is a very huge platform, the Apache Kafka alone handles 2.1 trillion messages per day, where zero point 0.5 petabyte are incoming messages and 2 petabytes are outgoing messages per day. So peta is 1,000 trillions, or 15 zeros after one. So it's like that much of incoming messages and that much of outgoing messages in compressed form. And then 16 million messages per second, and the peak times are almost there. So every second they have almost this much of messages. So Apache Samza is a battle-tested and scalable stream data processing framework. So we have data which is in real time and it's coming. So we need an effective processing framework, and Apache Samza is one of them. It is a top-level Apache project since 2014, and it is supported by giants like Netflix and LinkedIn, Uber. So these kind of big companies are sponsoring this Samza, and it powers hundreds of applications and LinkedIn productions. What is the goal of Samza? The first one is the scalability, where a job is divided into multiple parallel, independent, and identical tasks, and an input stream is divided into partitions. Then efficient stateful processing. State is any present data structure defined by the application are used internally in the system. It is composed of local and incremental checkpoints that we will see later in details. Then fast recovery and restart. After a failure, a job or a portion of it needs to be restarted. And unified data processing API, where the SAMSA drops a unified model supporting both stream and batches. In other words, SAMSA treats batches as a finite data stream. So application logic is developed and maintained in one place using unified APIs. So we will now see each one of them in more depth and detail. So the first one is the scalability. So the client streaming data is coming to the input stream, and then it is partitions. All the big streaming data is partitions into small chunks, and then all the chunks are coming to the SAMSA applications, and then there is a task processor. So each task is handling couple of chunks that we will see just in a while. Each dedicated task is taking care of the partitions that is coming from the input streams. So this is the processing unit, and the processing just process the data in real time and then it give it to the output. So it's also possible that there are co-partition stream. For example, one is the add viewing stream and the other is the add clicking stream, and multiple data of the co-partition stream is coming to the task processor. So for example, the add viewing one is coming to this one, and also the click stream data is coming to this one. And likewise, from the second partition, the data is coming to the second processor, and also from the second partition, that this coming to the this task processor. And uh, processing each one task, we have some meaningful data for each of the tasks. For example, what are the add click-through rate stream on the one and number two, and also on number three. So the multi-stage data workflow example is shown here. So in input, we have the page view in stream. So there are like the data in stream coming where the user has like how much number of clicks might be there. So firstly, they are partitioned. The data is partitioned into an intermediate stream is performed where the chunks of stream is there. And then those streams are monitored for some window of time. For example, for 5 minutes, those streams are monitored. So what is the task number one? Let's say this is the task number one, and how much clicks of as user is there. So it is monitored for example, 5 minutes. And then what is the mapping operations do? Mapping is taking that amount of data for 5 minutes and sending the relevant information to the output streams. So this one is shown in with the example how to do it encoding. So for example, we are using the stream applications to count what are the from the input stream, count what are the pages views per member. So firstly, the partition, the incoming stream is partitioned by the partition ID with a member ID, and then a window with some amount of time is monitoring that their tasks. And then the map is creating a new output stream, and then this information from page view per member is sent to the output stream as shown here. Now we have the efficient state processing, stateful processing. So let's see what it is. As I said, that the input streaming is coming, then some application is creating tasks for the streams. But before giving it to the output, it also stores the state of each task. So there is some database or memory which stores that tasks here, and also it gives the task output in parallel. In other words, we have local states for each task. For example, task one would have some local memory or local database here. Similarly, task two would have another local database, and it would store all the related state of corresponding to this task, like what is the number of clicks and what is the profile, the number of it. So all those kind of states are stored and individually in each memory. But the question is, how about failure? If any of the task fails, how to restore it? So we don't want to lose that kind of data. For that one, they have the change log. How the change log is working? Firstly, it estimate what is the current offset here from the streaming, and with the current offset, what is the, for example, here it is the page count example. So this task has like this much value here. So this value should be stored locally in this particular database. So this value is stored here. And the same is happening for here. With this offset, what is this current status? And that current state is updated to the other partition. And likewise for the KTH one. And alongside the change log, also the offset information is stored here. So whenever there is a failure of a certain task, we know that at this particular checkpoint or at this particular offset, the value of this particular task was here. And since it has failed, so restart the task from that particular state. So it does not support full-scale checkpoints, which means that if there are non-trivial application states, then it does not scale to it. However, still it make it easier to recover a task easily if a failure happens. However, it does support the incremental state checkpoints, which means it can scale to any type of application state to achieve repeatable results. However, it requires some additional techniques, for example, deduplication of data. First we start with the local state. So we this is durable because it incorporates task container host mapping. What is that? So since I told you that the SAMZA jobs are the input stream is given to the task, and then there could be multiple tasks in a single host, or there could be a single task in a single host. Assume that any task fails, then that particular task would not be assigned to a new host, because if it is given for this task 4 is failed, this task is given next time to the host B, then task 4 has to be restarted from the scratch. So it is avoided here. And there is host affinity technique used here, which means that if the task is failed here, that task should be retained again by the same host. And that's why it saves a lot of time by not starting the task from the very scratch. So what is the pros and cons of the local state? So the local state is 100 times has 100 times better performance, as we will see in a while, and it has no issue with the accidental denial on service on remote DB, since it is locally. So if there is any remote database error or something occurring, it is not depending on that, and it does not need to over provision the remote database, because it will have certain latency to go to the remote database and access it. What are the cons? When we have adjacent data is very large, then the input is not poor partitionable, and this does not work. And auto scaling also becomes very harder, and repartitioning the input system can mess up the local states. So this is the final part, the unified data processing API for this one. So if let's assume that the input is coming in the form of batches, that input is still regarded as a stream. So even if there is a lot of batch data available here, it will be taken by the SAMZA as a stream, and it will be still be compatible. So if the batch input is there, it will not be just discarded, but still it will be streamed and it will be processed as like normal one. So this is how a unified system works, so that it unifiedly work similar to the streams. And also if there are batches, in a unified way, it will be dealing the batches too. So here is the evaluation. For the evaluation, they use some small cluster with 6 nodes, and this is the specs like 64 GB RAM, 24 core CPU, and 1.6 GB SSD. And also they have 2 benchmarks. One is read-only workload, and the other one is read-write workload. So here is the firstly, they show the efficiency by leveraging the local state. What is the throughput? So the local states mean that the state is saved in the local memory or in the on the disk, and the local disk, and they are not using remote database. For instance, um, as an example, they have used remote database, and you can see that the efficiency is significantly dropped. The throughput is very lower for the remote database accessing, because it requires extra latency when when the remote database is away in some other country, and end-to-end latency will be too much. So if you look at the green one is the maximum read-only maximum network utilization for read-only, and the black one is the maximum network for read-write only. So in memory, if you see both in memory and on disk, they have almost the same throughput. It almost reaches to the maximum. So this one blue corresponds to the black one, and the red one corresponds to the green one. So we can see that the read write is almost achieving the maximum here too, and also on the disk. However, when we use the change log mean that we use the fault tolerant system. Then with that overhead, a slight degradation happens, but it is still not that much significant. So you can see that there is slight degradation in both with the in memory and also on the disk. And the red one is same, but it is for read-only operation. Since read-only operation peak is the maximum is green, so it is also consistent even with the changelog and also without changelog. So there is no significant difference. Why this is different? This is different because it has no cache. So since it has no cache, so there is no buffering, and because of lack of buffering, it has degraded performance. And what is the local state latency? So if we look at all of them, the SUMSA, if we look at all of them, the read-write operation is very best if we are using local memory. For example, local memory or local disk, we have very low latency. But even if we are using the change logs like the fault tolerance system, still we have low latency. But if we don't have the database, but if we don't have the buffering, then the latency a bit increases. And if we don't have, and if you are using the remote database, then it increases a lot because the latency for accessing a remote database would be higher. And finally, they have the execution time with their rivals. For example, this is blue one is SUMSA, the red one is Hadoop, and the green one is Spark. And we can see that the SUMSA outperforms every other rival. For example, Hadoop has a lot of execution time required, and same as for Spark. But for 100 number of containers, SUMSA outperforms both of them. Also, when the number of containers increases, the SUMSA efficiency is still better than the other one in terms of execution time. But the other Hadoop and Spark efficiency increases when we increase also the number of containers. And with 500, still the SUMSA is better. So to conclude this, we have the Apache SUMSA, which is scalable. It has fast recovery and restart. It has efficient stateful processing, and it has the support for unified data processing API. So what is the novelty of this work? So the novelty is it is a framework with 100 times better performance than its rival. It is scalable plus fault tolerant plus unified and efficient stateful processing. And my impression is since it is like supported by big giants like Netflix, LinkedIn, and a lot of people, so it's a very effective and impressive work, and I like it. So that's all from me. So I'll take your questions if you have. Thank you.